What is the most used man-made material on Earth? You guessed right, it's concrete. Look around. It's everywhere. Sidewalks, driveways, foundations, floors you stand on, and even entire buildings are made out of concrete. So why don't we discuss it more? In each episode of Concrete Logic, we will explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future. And welcome to another episode of the Concrete Logic Podcast. And today I have Bill Kulish with Steelike. Bill, could you please give us a little bit of introduction to yourself and Steelike Concrete?
Sure, Seth. Thanks for inviting me on your podcast. I'm Bill Kulish. I invented Steelike UHPC. Took about 15 years. My background is I'm not a mechanical engineer. I'm somebody who was doing a lot of decorative concrete, countertops and architectural panels, and wanted a material that required less post-production. And I've read about UHPC and the fact that you just place it and you're done. You don't have to grind it, wet polish it, acid wash it. And it seemed like a good fit for my business. So in the beginning, I named my company Kulish Design Company, and it was more architectural detail focused. Spent 10 years there and came up with, through a lot of pain and investment, came up with UHPC, and I wasn't even aware of it at the time. Went to the world of concrete, and a gentleman approached me with 5 people and said he was with an organization, air quotes, and he said, I heard you have UHPC. We've been working on UHPC. What's the biggest batch you've ever made? And I was all proud and said 700 pounds because I was making a big countertop. And he said, well, we would need about 200 cubic yards to test this stuff out. Is that something you could do? And of course I said yes. And then I found a blender to do it and went down, and turned out it was Fort Knox, and they were doing some testing on UHPCs. And that was the beginning of me getting into infrastructure versus decorative concrete.
Wow. Yeah, that's a awesome first client. Understatement of the day.
It was a little overwhelming, but it was all good. And full disclosure, I thought it was a friend trying to mess with me, but things started happening, and next thing I know, I'm down there, and we're mixing day after day after day, and the word got out that I had something I wasn't aware I had. And then the FHWA was doing a girder prototype, and Steelike was selected as one of the materials to do 35 and 60-foot girders. And then the DOTs, it was successful, and the DOTs found out about it. And little by little, we started getting solicited and began soliciting. And here we are today with well over 50 projects under our belt, and the business is growing quite well.
Awesome. Yeah, so for our listeners, let's back up a little bit. And the reason I reached out to you, Bill, was I was looking for someone that could come on the podcast and kind of give us a definition or a background on what ultra high performance concrete is. I've seen videos on LinkedIn, and you have one we were talking about before we hit record. Very interesting video on guys doing some bridge repair. So could you, I guess, explain to us what this UHPC is for us who, like me, I've only, I guess, worked with normal concrete for the most part. I've done some self-consolidating concrete in my past, so that kind of reminds me of that. But could you explain what it is?
Absolutely. It's more of a composite than it is a concrete per se. A lot of people will say it's mortar. It's not It's not traditional concrete. So the biggest characteristics that make the differences are, number one, it's all based on particle packing. So particle packing, you take a 5-gallon bucket. You can only fit in so many softballs. You take out some of the softballs, you put in golf balls. You can fit more golf balls than softballs. You take out some of both, you put in marbles and BBs, and you go all the way down to a sub-micron level. And what you're left with is an extremely dense, highly reactive, cementitious material. The largest aggregate is 400 to 500 microns. So we don't have those 3/4 inch stones. The rocks, the stones are the weak point of traditional concrete. When two 3/4 inch stones hit each other and you put a load on it, you create a fulcrum, a lever. And the stones literally create the internal destruction of the material. So UHPC gets rid of all that. Instead of a 3/4 inch stone, you may have thousands of pieces of different size and different shaped sands. Now you add a little bit of water. So the water cement ratio on average is well below 20. The stuff you guys drive on the way home is probably a 40% water binder ratio. What does that mean? You divide the amount of water into the cementitious or the binders, and that gives you a percentage. So the water cement ratio is really low. And as most people know, the less water you have, the stronger you get. One of the other interesting things of UHPC compared to all the other concretes and mortars out there is we purposely engineer it by starving the water. We engineer it to leave unhydrated binders. So what does that mean? Well, that means they're not activated. So if it starts to micro crack and it gets wet, it recrystallizes. It self-heals. Now, if you blow a 6-inch hole through it, you spray it with a garden hose, the hole's not going to close up. But the material itself is very brittle. The compressive strength is off the charts. We've autoclaved Steelike and it's over 50,000 PSI. Yay, that's a big number. But it's worthless in the real world because you have a 50,000 PSI material in your china cabinet and you drop that thing, it's going to explode. So how do we deal with that? How do we make it less brittle? We put in steel fibers that have an extremely high tensile strength. So when the crack initially occurs, it's microscopic. It hits a fiber, it becomes more microscopic. No concrete bends without cracking. All concrete cracks when it's being flexed. But because UHPC doesn't have big rocks, because UHPC has such a high fiber content, high tensile fiber content, you put a load on it, you start to get microscopic cracks. They're so small, water will not get into them. Then the load eventually opens a visual crack, a macro crack. The load transfers to those fibers, and then it goes back to the binder and back to the fibers. So you get a very interesting curve. The load is applied, you get your first crack, it drops down, transfers to the fiber, goes back to the binder, down, up, down, down, and you actually get strain hardening. Where most concrete goes up, it cracks and it fails. This will go up and crack just like steel, come down, transfer, up, down, up, down, up, down, and it gives you and your family, if you're on a bridge in an earthquake, it gives you that time you need to know something's happening and get off the bridge.
Huh. So it's almost self-healing at times? Is that
It's self-healing to the extent, again, a 6-inch hole with a garden hose isn't going to close up. But as the material cracks, and again, in the beginning, unless there's a tremendous long-term load on your structure, you're always going to get microscopic cracks. But those cracks, if they get exposed to additional water, will recrystallize and self-heal. So yes, it's self-healing, but no, it's not magical close up large gaping holes.
right? No, normal wear and tear on concrete, I guess, is what I was referring to. Cracks that happen and not massive holes or or abuse that may occur to it. So so it's different than normal concrete, and it's not mortar. It's so what, without giving away the recipe of what Steelike is, what is in UHPC versus what's in concrete? Is there a lot of admixture, to offset the necessity of water, or what I guess what is it made of?
Well, we have binders, and the binders are 40 to 50% of the entire mix design, and this would apply to everybody's UHPC. The additional ingredients, other than unicorn horns and things like that, which we can't talk about, the additional ingredients would be different binders. They could be post-industrial waste. A lot of companies use silica fume, ground quartz powder. If you grind something small enough, it can become reactive. The high range water reducer or super plasticizers, many companies add it as an admixture at the end. Steelike is just add water, so I already have that into the dry ingredients. Other things that would make it different from regular concrete, or what is UHPC, highly reactive, like an ECC. That's kind of where it ends with comparison to ECC. So we would have regular concrete, water binder ratio, water cement ratio might be 30 to 40%, stuff we drive on highways. You might get 4,000, 5,000 PSI compressive strength. UHPC, 20,000 minimum. The Federal Highway Administration is currently at 18,000 PSI to qualify as a UHPC. It's impervious to chlorides. So you could take a block of Steelike or other certified UHPCs, throw it into the ocean, come back in 1,000 years, power wash it, and it would be the same as when you threw it in. That same cubic foot could have a shiny steel bar of high carbon bar inside of it, and that bar would be as it would be fossilized. So we get something that, oddly enough, loves abuse. If you freeze and thaw Steelike 600 times, it actually increases it in properties versus going in the other directions. It's innocuous abrasion resistance. It'll wear out the machine that tests the abrasion. Its impact resistance is off the chart. Why? Because we have all these fibers, and you hit it with something, and it transmits the shock waves throughout the matrix of the mix.
Wow. So why don't we use UHPC for everything then? If it sounds
way
like
too expensive. Yeah, it's just wait, Seth. It's relatively speaking very expensive if you just look at doing a slab with UHPC versus traditional concrete. Here's where it starts to offset a little bit. It would be overkill. You're not going to see UHPC on all roads throughout the United States. It would just be too expensive. The advantage of it is you can make structures that are 40% less in mass. You can, if you're digging a tunnel, you have to remove that earth, and you could remove 40% less earth, which means you don't have a bunch of fuels burning to get the stuff out of the tunnel. You could then line it with a shell, a lining that would be 40% less than what it would normally be. If it's 3 feet, it would be a lot less thick. It's only going to improve in time. It can handle tensile stresses dramatically better than traditional concrete. The list starts to go on. So you're using less. You have less of an environmental impact. Yes, it's got a high binder ratio, but you're using so much less of it that it starts to offset the cost of it. So where they find it shines is connecting things, protecting things, encapsulating things, restoring things, preserving things. And we can go on to a bridge that otherwise would probably the deck would have to be ripped off and replaced. There could even be exposed bar starting to rust. You would hydro demo the whole surface, put down about 2 inches of UHPC, and that bridge, it's good for another, certainly much longer than 100 years. The average life is 50, 60 years. So now we've doubled the life expectancy. So yeah, we spent a lot of money up front, but when you amortize it over the value and how long it lasts, the endurance, it starts to line up a little better.
Okay, so it's probably a better product for more, like you said, the bridge repair. So repairs and restoration and things like that. What other applications does it make sense to use UHPC?
I can speak for what Steelike's done, but this would apply to majority of the suppliers in the United States. We've done steel end girder repairs. The Delaware Memorial Bridge, one of the owners is a engineer, and he designed a way to encapsulate what would otherwise have to be ripped out and replaced with steel. So steel end girder repairs in a SEPTA tunnel by 30th Street Station. They had these giant steel girders, 30, 40 feet, suspending a bridge above it. And with live train traffic, we're one of the few companies that have, since 2015, have always mixed and ready mix trucks. We mixed up on the bridge. We dropped it through a 70-foot tremie, and they built these cubic meter or very large boxes around the unearthed, failing, rusting girders. And we filled it up with UHPC, and that thing's good for multiple centuries from now on. So encapsulation, preservation, overlays we talked about briefly. There are some architectural applications. A company called Tactile focuses on that. They'll do giant, thinner panels that are normally require 3/4 of an inch with GFRC, glass fiber reinforced concrete. You can do it with UHPC at a 1/2 inch. And because of all the characteristics I referenced, the weatherproofing, salt, chloride, so on and so forth, that's been utilized quite often. So we talk overlays, connections, ABC, accelerated bridge construction. We did a project in West Virginia. Friday night, they ripped out the existing deck. They had already precast some 5,000-6,000 PSI traditional 8-inch slabs. They dropped them in on Saturday with cranes. They left 8-inch gaps between all the dominoes that they dropped on the existing structure, and UHPC was brought in to connect everything together. So it eliminated a lot of expansion joints. It reinforced the deck dramatically. The place that was failing was where chlorides got in and started rusting the internal bar, right? So by doing this system, that bar is now fossilized for all time. And it doesn't matter if they dump salt on it or not. Freeze thaw doesn't matter. And the ductility of it, because of the fibers we talked about, Seth, allow it to kind of move like a living organism instead of being trapped.
Yeah. That video you posted on LinkedIn with the guys working on the bridge, and you were saying that you're one of the few since 2015 that mix in a truck, the UHPC in a truck. And that was what the video was, right? Of a guy, the truck was driving along with the chute, and you were dropping it in it looked like maybe 8-inch wide gap. Yep. And what were they doing in that video? Could you explain that? And I guess start with, is the mixing UHPC, is it very like just normal concrete as far as that process, or what's the process if you're mixing a batch in the back of the truck?
It's a little more challenging, Seth. Yeah, you are adding water, but as we talked about, very little water. There are no stones or aggregates or rocks, and that helps mix it, right? Because you got these rocks, you get that mixing energy. The rocks are in essence little paddles. Well, now you're taking all that away, and you have this extremely fine, very small aggregate material going in. All UHPC is mixed. It's the antithesis of what we all grew up with. Normally you add your water, then your mix. All UHPC, to be correctly mixed, you add the dry material first, not the fibers, just the powder. Then you add your water. then if some suppliers will add mixtures at that point, we have ours built in so it's dry. Then you turn the stuff, and when you see UHPC mixing, it looks like failure is guaranteed to happen. It happened to me for 4 years. I was burning out hand drills thinking I didn't have the right mix, when in reality I didn't have the right amount of torque. So as you add the liquid to UHPC, it sucks all of that in. It doesn't have any water, and it'll turn into, first you'll see BBs, moist BBs, and then moist marbles, and it'll get bigger and bigger, and then it'll just flop and turn into this thixotropic, looks like pancake batter, at which point you'll add the fibers. So the mixing in a ready-mix truck, many companies started that way. The biggest company started that way 20 years ago. And when I talked to them why they're not doing it, they said it takes too much time. And there's videos of lumps of fibers and lumps of powder. It took us about 4 years to figure out the sequence, the speed, where the water's added, how it's added, what pressure it's added at, how to monitor the temperature, when and when not to use ice. But we dialed it down in 2015, and that's the only way we've been mixing it. Now I have 2 patent pendings on a pumping shotcrete spraying system, which has its own mixer built in with proprietary mixing equipment. Other companies will use modified vertical shaft mixers, and you would, if you were the client, the contractor, you would pay to rent them. They would ship them to you, and you need 2 little power plants, and they're stationary. They take about a half day to set up, and they're about, the max capacity is about 1.4 cubic yards. Our model was to focus on mobility. Anybody can rent a local ready-mix truck. It could be front loading, rear loading. And we set up a platform and we do the mixing there, and then we can drive up to, we've gone 2 hours away from where we mixed it to placing it.
Wow. Is there any testing done with, like, that bridge work you were doing? Do they do any testing on it, or what? Yeah. How do you determine it's good to go?
They have to do that, and it's in all the contracts. So the bridge owner, it could be privately owned, state owned, so to speak. A DOT, we'll do a DOT example. Although Brightline's privately owned, so we can do that one too. They'll engage a consulting engineering company. They'll design the spec to use UHPC. They'll then say must be tested, and the way it's going to be tested is you have to check a bunch of things before you even go near the project. You have to submit a lot of data that was done by AASHTO and ASTM accredited labs, independent labs, and we have about 15 years of that. You get them that package, and they're like, great, we trust you, but trust but verify. So when you're on the bridge and you're actually placing the material, they're going to pull cylinders. They're going to do a flow test, and they're going to pull a lot of cylinders. Some owners, bridge owners, will allow the maturity method, where they'll put in probes into the material on the bridge and then make some cylinders and put probes into the cylinders, and we've done it. All the major suppliers have done it. We now know when Steelike is 140 degrees, blah, 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 that it's X amount of PSI. But they'll always want confirmation with cylinder breaks. And that can be a nightmare. There's only a handful of labs in the United States that understand testing this material. We use a lot. We use 5 of the 7. We're about to engage 2 more. Why is it unusual, Seth? Well, you're making your cylinders, but the first difference compared to regular concrete is you're making 3-inch by 6-inch cylinders. And the cylinder preparation is huge. If you don't put it on a vibrating table, you don't rot it, it could segregate things. So you fill the cylinder almost like you're filling a draft beer. And then you want to do it in one contiguous fill. And then you're going to top the outside of the cylinder 30 times with a rubber mallet. Then you got to get the lid on, and there's metal fibers. So if you just shove the lid on, the fibers will prop it open, and all the water will evaporate. let's say you make it through that. Now you got to get it to the testing lab. Then they have to use $20,000-$30,000 end grinders that will grind the ends to be perfectly perpendicular and parallel. If that's off just a little bit, you'll get a shear break. And we've seen shear breaks artificially low. When it's done correctly, they're going to load it in the compressive machine at 145 seconds PSI per second. So there's another difference. So the cylinder size is different. The preparation is different. The grinding preparation at the lab is different. The rate in which you do what you do is different. And then you have data. And that data gets sent back to the bridge owner so that the engineers can say, thumbs up, we're good to put traffic on my bridge or your bridge.
That seems to be a lot of effort to put to test UHPC with our the ways that we test traditional concrete. Do you think there's better ways to test it to see if it's doing what it's supposed to do versus that effort?
The maturity method. Once the maturity method gets embraced, it's all based on science, Seth. It works. The great thing about science is it doesn't care about my opinion, your opinion, anybody. It is what it is in this case. We're talking about concrete, not existential things, but it works. So and it's been repeated over and over and over again. So you make some cylinders in your lab. You stick some probes in some sacrificial cylinders. You put some in a cold box. You put some in high heat. You put some at 70 degrees. And every X amount of hours, let's say 6 hours later, you pull out a cylinder that says it's 120 degrees and you break it. And you correlate the strength to the internal temperature. And it's so predictable that, we've gotten within 3-4%. So now you're on a bridge in the Antarctic. You're not going to be flying these things down to a lab that has a grinder. So you know through enough repetitiveness and historical data that when this material is X temperature, it is this strength. And by the way, here's the data and the broken physical cylinders to show it. And you do hundreds of these things, and you can predict. You could be sitting in a hotel room with the right app and sensor, and it'll take that equation, and it'll tell you what the predictive strength is. Hey, it's 12,000 PSI. Good, I can sleep for another 2 hours. So that's coming. And I know the big guys, our competitors, we're all trying to promote it, but the industry tends to move a little slow to change. So right now, you can UPS a box of cylinders anywhere you want. So right now, if there's not a qualified lab locally, it gets put into a controlled cooler. It's moist. It gets shipped. And we've had stuff shipped from Florida up to Chicago, next day air, and they do the early breaks.
Yeah. Is there any other things to check other than compression strength to make sure it's doing what it's supposed to? And that sounds. That effort as far as maturity, the maturation technique with the meters and everything. That's going on with traditional concrete as well. We can't get folks on board with traditional concrete, and so to get it for a product like UHPC, which isn't universally used right across the board. So even to get people past that point as far as using UHPC, and then trying to get them to use a testing method that they don't like to use with traditional concrete. That's a lot of ask, I think. Is there other things? Like, is there moisture content? It doesn't sound like there's a slump. There's no slump on. This thing is when you like you said your analogy earlier about it being it looks like pancake batter. That hit the nail on the head. That video that's on LinkedIn, that's pretty popular, that you posted. That's what it looks like. It looks like pancake batter. It doesn't come out like concrete, like normal concrete. So, so is there other things that you need to check? Moisture, anything like that?
what's happening, Seth, is because of everything we just mentioned and the challenge. You're on a bridge in the real world. It's 3 o'clock in the morning. There's nobody around other than the contractors and the mix supplier. There's QC is the answer. The reason you and I don't see UHPC and Home Depot, let alone all over the United States, being mixed by 50 different companies, although it's coming eventually, is quality control. So you can't just go to your backyard and dig up some dirt and sieve out the sand and throw it in. Unfortunately, you can't just go to a local brickyard and say, give me that orange sand that's sitting outside. Why? Because it's got minerals and iron and reactive stuff, and there could be a silica react. There's all kinds of issues with that. Moisture for sure, dirt, iron, which could react to the steel fibers, and then you create hydrogen gas. I mean, the whole thing gets crazy. So the ingredients have to be so controlled. The average contractor or precast company, they might be paying $20 a ton for sand. When you get into the UHPC world, it could be $200 a ton. Why? Because it's washed, sieved, kilned, specced, taken out to dinner. It's given roses every Valentine's Day. The sand has to be so consistent, because otherwise it just blows apart the recipe, and now your water demand can go way up and down, and now you have no idea of predictability. So of the major, there's 5 in the United States right now kind of doing infrastructure. We're one of them. We all have materials sitting in storage to compare if there's ever a challenge or an issue. It's QR code in my case. We hold back 20 pounds of every batch, put a QR code on it. So if somebody says, I think we got defective material, it could be a lab that doesn't know what they're doing. We'll send that material that matches the material that was placed on the bridge directly to a certified lab, independent lab, to confirm that it is indeed good. But to answer your question, it's all done up front. So the moisture content, everything but compressive, and there is a slump test. It's just done in a very unusual 10-inch brass plate. All the other tests are done ahead of time, and it's matched with the material. So, and there are 52 different tests that have to be done to get on a bridge in the United States with any kind of federal funding. So we have to check all those boxes ahead of time.
Gotcha. Well, that makes that connects the dots far as why it's so expensive. so it's very the ingredients in there are scrutinized a lot more than your traditional concrete. Sounds like it goes through a lot more. So that's why we're not seeing, like you mentioned before, slabs poured with UHPC. It's smaller quantities. What's the largest quantity that you've done so far?
We've done 500 cubic yard projects. The Delaware Memorial Bridge was just done by one of my competitors supplying the material. That was 4,000 cubic yards. It starts to make sense because you're amortizing the cost of setup, getting on the bridge location. If you're doing this little tiny project, it could be extremely cost prohibitive. The bigger the project, you're still utilizing the same amount of equipment and setup and such, traffic control, and you start to amortize that in. It starts to become more affordable when you look at long-term life. So again, the upfront is like, wow. And you're absolutely right, Seth. I did say that we're not going to see highways done with it. But we will see a lot of overlays in harsh environments, on critical mission bridges that go in and out of major metropolitan areas, freeze thaw environments. Florida's got salt everywhere. And you start utilizing this material the right way when it's needed. It would be overkill to make a 6-inch slab out of it. It just wouldn't make any sense. Maybe a heavy aircraft or a recycling area where they have giant trash dumpsters and such, it would make sense to use UHPC. You're going to pay a lot more up front, but you're not going to be replacing it every 5 to 10 years. So there's places where it makes sense, connecting things together, overlaying them. We can go with our shotcrete UHPC machine. We can go to a failing column in a caustic environment with exposed rebar and spray this material over it. Once you encapsulate any structure with any good, true certified UHPC, you fossilize the damage. There's no more chlorides getting in. There's no more water that can get in, so the water can't freeze and it can't thaw. So it makes sense when you use it where it makes sense. It's illogical to just build a skyscraper out of it. It would be so over-engineered, it would be ridiculous and very cost-prohibitive.
Gotcha. So it's not going to be used for 3D printing or anything like that in the future?
Well, no, I'm going to stop you. I'm actually flying out to the West Coast to utilize it for 3D printing because of everything we just said. Less material, all the characteristics, impact, abrasion resistance, freeze thaw, chloride permeability doesn't happen, and it just the list keeps going on, and it's so dense. No, it can be utilized for that. You would just use less of it. But the video that you saw on LinkedIn that we talked about, I only have one recipe. The only thing I change is the amount of ice, the amount of water. So that material with less water would be used for an overlay. That material with less water and a thickening agent would be used for 3D printing. That material with a little more water could fill up any void, thanks to gravity, and get in there and still have all the characteristics we talked about. I mean, think of it, a hair on your beard might be 300 microns. That's the biggest thing in there. So it's going to go in and fill every joint, every nook, every cranny. It's going to wrap around and bond. The bonding characteristics are insane. If you take a true UHPC and you fill a 5-gallon bucket with it, you put in any size diameter bar, and you put it down about 4 inches developmental length, and you wait until it's got some strength, and you try to pull that bar out, the bar is going to snap. So this stuff, UHPC, bonds to everything. Case in point, we're at Iowa State University. You'll like this. We're launching the shotcrete application, and a professor and a mentor of mine, Cherie, he's known for his UHPC expertise. He says, I'm going to build this column and we're going to spray it with UHPC. So we put it on a Lazy Susan and we're, work smart, not hard. We're rotating the column. I'm standing stationary up and down this 10-foot column, and it went over the backdrop. And I have a Ford F-150. I just had it washed and waxed, and it's white. Somehow these splatter drops hit my Ford. I don't see them. 2 weeks later, I come home, I'm washing it. My rags are ripping. I'm like, what's this? And I realize it's UHPC, little tiny balls. I'm like, what's the big deal? And I try to pop them off, and it rips off the wax and the clear coat. So I don't know. Again, I'm not a material scientist, but that tells me this stuff bonds. And now you do that to metal or anything else, it's going to grab onto it. So there's another advantage of UHPC.
So we didn't talk about the steel fibers in it. Then they got to be very, very small, right?
Yes, sir. You're looking at, I'll reference your beard again. You take a half-inch piece of your beard. That would be the biggest they would be. They are extremely high tensile, high carbon. They're brass coated. They're brass coated not for the reason of being used in concrete or UHPC. That's the lubricant. So they start off with a rod and they're drawing it down. And you have a couple choices, but brass is a lubricant. So it's got this micron coating of brass, which goes away immediately when you mix it. Very high tensile, anywhere from 200 to 400,000 psi. They're hypodermic needles without being hollow. Everybody hates them, but they work. At least as of now, that's the only fiber that gives you the strain hardening characteristic we were talking about.
Huh. Why do they hate them?
Because they'll stick in your shoe. They'll get in your clothes. They'll go right through your finger. So they're hypodermic needles without being hollow, and they're 400,000 psi tensile strength. So they're not loved by anybody.
I gotcha.
But they work.
Gotcha. So you got to be careful to use them. And so I assume there's probably folks trying to figure something else out to use, or that maybe less caustic.
They're trying, Seth, and I'm smiling and you're smiling because I'll go right back to your correct statement about maturity method. I have 100 pounds of a monofilament of a different material that is not steel based sitting in my lab, and I got so excited. The testing shows they're better than steel, but unfortunately right now they're $40 a pound. So that ain't going to be happening, and nobody's going to pay $20,000 a cubic yard for a material when they can use existing recycled steel belted radial tire wire, bicycle tire wire, and it's forged in the United States, melted, kill everything, and then it's sent to a place in a drawn wire on a spool, and they chop it. And that's the other thing. It's got to be Buy American Act steel in the majority other than privately owned properties, right? So that when you mention the price, and I'm never going to defend, it's very expensive. Almost 2/3 of that is the fiber. So when you're looking at X amount per cubic yard, you're putting in 265 pounds of fiber per cubic yard.
Oh, wow.
And the fiber can be $2 to $3 a pound. So you got $700-800, if not more, of just the fiber. But there is, as of now, there's not an affordable alternative that gives us the strain hardening.
Gotcha. What's the total weight of 1 cubic yard of UHPC?
They all range within 100 pounds. Steelike is 3,600 pounds of dry material plus liquid will net in volume a cubic yard. Some of the other guys might be 150 pounds less, 50 pounds more, but on average, it requires 3,600 pounds of dry material. So the PCF per cubic foot of the average UHPC with a 2% by volume load, which is what's used for everything but overlays, would be about 150 to 153 pounds. Now, when I tell people that, they're like, well, that's not that dense compared to regular concrete. Go back to that 3/4 inch rock. It's now got thousands of pieces of sand. So it's a different type of density.
Mm-hmm. Yeah. Yeah, it's different. It's different. It's definitely different. But
it's weird stuff. Weird stuff.
That's right. But it's interesting. I think that's a good spot to pause today. We'll definitely get you back on to talk about this more and be interested to hear what you come up with after your visit on the West Coast about the 3D printing, and if there's an application there that we can discuss down the line. If folks want to reach out to you, Bill, and learn more about Steelike, what's the best way?
They can go to bill@steelike.com. Go to our website, steelike.com. It's like steel, one word, one L. That would be the easiest, Seth.
Yep, and on LinkedIn as well. And we'll put your contact information on the show notes so folks can reach out to you. Bill, I appreciate you coming on the show today, and I look forward to talking to you again.
Anytime, Seth. Thanks for the invitation. I look forward to future conversations.
All right, thanks. Thank you for joining us for another Concrete Logic podcast episode. If you got some value out of this or you enjoyed it, please share it with others. And if you could take a moment and give us a 5-star review on your favorite podcast listening app, I would appreciate it. We will catch you on the next episode. And now Mike Dunton's going to take us out.
That alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and hard to get that job done with work.